Okay, so I think that Paul has joined. So for those of you who are here, hang on for a second. This is the first time I've done this, but we're going to be talking about climate science today, and I'm bringing on some experts to help me talk about it. And so I need one more person to join here. So I'm waiting for him to join. In the meantime, I can introduce myself and who's here. Oh, it looks like we're all here now. All right, we're all set, hopefully.
All right.
Okay.
I'm not sure.
Yay, we're all here. Okay. Well, welcome everyone to Energy Live. This is a great opportunity for us to talk about some of the great science that we're doing at the Department of Energy. My name is Charlene Weatherwax, and I'm the Associate Director for Science for Biological and Environmental Research in the Office of Science. And so for those of you who may not know, Office of Science is a big supporter of climate science, and especially the research that's needed to underpin the kind of decisions that you want to make when you want to understand how can we respond to what's happening, with climate. What is happening with climate? So I'm joined today by some experts who can actually speak to the kind of work that we do, which is really underpinned by modeling. Since we can't actually make climate, we have to kind of model it. And so we have experts here who model it from a variety of different perspectives. And so they're going to talk a little bit about their work, and we're going to try to answer some questions that come up, and we'll just have a little dialogue about it. So I want to briefly introduce my guests, and then we'll just start the ball rolling with the discussion. So the first guest I have is Dr. Ruby Lung. She's with Pacific Northwest National Lab. Hi, Ruby. I also have Professor Paul Ulrich from University of California at Davis. Hi, Paul. And then also Rao Koldamarti with Argonne National Lab. Hi, Rao. Okay, so each of you, works on modeling in a slightly different way. And so why don't you kind of describe your own sort of spin on it? And I guess we'll just start with Ruby.
All right, thank you very much. I am a climate scientist. I use computer models to study how human activities affect climate and what this means for the natural resources on Earth and our ability to use and manage the resources. I am particularly interested in how global warming affects extreme weather events, such as thunderstorms, and also how much water will be available from precipitation and mountain snowpack.
All right. Those are big things happening. It's not raining here now, but certainly precipitation is a big what we experienced. So Paul, tell me about what you do.
Hi, everybody. My name's Paul Ulrich. I'm a professor of regional and global climate modeling at University of California, Davis, and work very closely with the U.S. Department of Energy to develop, run, and analyze climate models, and then use them in order to answer particular questions about the potential impacts associated with climate change, as well as get a deeper understanding of the processes that govern the Earth system.
And some of those processes are what you're shown in the picture right behind you there.
Yeah, you see this beautiful picture here of Hurricane Dorian, and it's just a reminder every day of the kind of impacts that we're trying to simulate and understand so that we can give people on the ground the best possible advice on how to prepare for these events, long-term and short-term.
Great. All right, and Rao, you want to introduce yourself and what you do?
Yeah, I'm Rao Koldamarti. I'm a senior scientist at Argonne National Lab. I work on two primary areas of research. First is understanding the effect of aerosols, the type of aerosols that are primarily produced from combustion process on Earth's energy balance. The second area of my research is that I will be talking mostly about today is focused on developing climate model-based projections of climate change impacts and climate risks. So these climate risk estimates are developed for extreme events such as droughts and floods. And my interest is at spatial scales of interest to communities to support development of plans for adapting to these changes and building climate resiliency. So that's my area of research.
Great. So each one of you has described kind of a different component about climate. And so I understand that a lot of it is modeling, but what exactly feeds your models? I mean, models sound very theoretical, sound like a lot of math, but what's kind of underlying it, and how do you get that information? How do you get that data? And I'll start back with Rao.
Yeah, so I actually I kind of focus on getting to the process scale, most with aerosol processes. Like there are a particular type of aerosols in the atmosphere called brown carbon and black carbon that are produced by the temperature you would burn some fuel. So the data we collect comes from ARM, Atmospheric Radiative Measurement Program, which is one of the flagship facilities run by the DOE BER program. And we do very focused field studies where we collect the process scale, everything from the burning of the fuel all the way to how it gets to the atmosphere, how it transforms, so that we can model this entire cycle and understand where the uncertainties are and how we can develop better models for these processes in a climate sense. Yeah.
Okay, how about you, Paul? Where do you get your data?
Well, we get it from all over the place. We rely on NASA satellites. We rely on the ARM program, like Rao mentioned. We rely on in situ stations, basically like weather stations that are stationed all across the world, where we can get measurements of rainfall, snowfall, temperatures, and all of that data feeds into building initial conditions and as well as deepening our understanding of the underlying processes. Once we understand that basic physics, then we can implement these mathematical equations into our computer systems. So much like a big video game, basically we have a huge array of underlying mathematics that basically underpins our understanding of the climate system. And these big supercomputer models that we are running then basically execute those equations or run them forward in time so that we can make predictions and projections of the future climate. So a lot of the data that I analyze actually comes out of these climate modeling systems running a variety of experiments. Obviously, we can't experiment on the Earth system. Various political groups, of course, would be very opposed to that, I would say, and countries, obviously. Generally, we don't want to experiment on the Earth very much, but we can run these climate models in order to run the experiments that we want, and we can then take the data from that in order to get a deeper understanding of what exactly is going on with the Earth system, and then answer those pressing questions.
Okay, so Ruby, I know that Rao and Paul have talked about modeling, but I know the kind of modeling you do is really high resolution. And so can you describe a little bit about what that means and how what you do, and also, has there ever been a time when it was, it didn't really work? You were working on your model and everything was fine, and then something didn't work out? Because it's hard to do, right?
Doing modeling is always a big challenge. And as Rao and Paul already talked about, so in order to build our model, we need at least two things, right? One is the theory. We have the equations that we know that govern how the air moves, how the ocean circulation moves, and things like that. So we solve these equations, but we also need to go out and collect data. And I have been quite fortunate to have this experience of doing both. I have flown on research aircraft where we fly through clouds and collect data of the tiny little cloud particles, and then we use the data to improve our models. But as you said, a very important part of our research is really being able to take advantage of the high performance computers, or what we call supercomputers, provided by Department of Energy. So with these computers, we are able to run our model at very high resolution, the kind of resolution that you need in order to really resolve the fine scale details that matter for how the Earth works. Like, for example, in the atmosphere, we have these clouds and we have convection and turbulence. All of these processes happen at very fine scale. So the higher the resolution you can run your model, the better ability you have to resolve these processes and make your model work better to replicate the Earth. So using big computers from Department of Energy is part of what makes our work unique. And then also collecting the data and the information that fit into the model and using the data to evaluate how well our model perform. And that's also very important part of building confidence about our models.
So when models are built up of lots of underlying components, right? We've heard about process models and sort of models at various different scales. So how do modelers work together to make sure it all fits together? Do you guys kind of all work in isolation? Do you how does that part work? So maybe I'll ask Rao.
Yeah, I mean, I've last few, maybe about 10 years now, I've been focusing on the climate impacts and trying to help people figure out what to do with the data set. So the biggest challenge for me has been to find this translation spot. So there is all these real great climate data products that are produced. How would that be used for somebody who was trying to, for example, say, develop an adaptation plan or build a resilient community? So this has been a challenge, and this requires that I work actually with people, not just like me, who are doing physics modeling, but people who actually talk to people or talk to actual people, which is very interesting experience, because the demand, if you talk to a community of people who are interested in this, they have a different point of view of what actually they think of climate and how climate affects them. So translate that into a question that I can use as a scientist, then to go back to my team and all the other people. There's a big set of people here who do physics, chemistry, biology, atmosphere, and humans now. To bring it back to a question that you can then answer with your model is becoming like a very, very interesting challenge. And I think that's what makes it really, really a lot of fun right nowadays.
How about you, Paul? You must work with a lot of different kinds of people too.
Yeah, absolutely. One of the advantages of working with the US Department of Energy, I would say, is this opportunity in order to really bridge theory and application. And so we actually have a project where we go out and work with water managers in order to identify their needs in terms of climate data sets, and then talk to them about where they think the biggest gaps are, as well as giving them our understanding of which climate data products are perhaps the most relevant for their purposes. And so with that in hand, we can then work together, both scientist and stakeholder alike, in order to address both questions of importance for them, as well as addressing gaps in our scientific knowledge.
That's great. So you're a professor at an academic institution. So where do your students come from? Like, what kind of backgrounds do they have if they want to do what you do?
Oh, they're all over the place. I got students from physics, computer science, applied math, generally from the physical sciences, atmospheric science, earth science, generally anybody with an interest in trying to deepen our understanding of the Earth system overall. And these are students that feed into the national labs, and they take up research positions at some of the labs that I work with, like Lawrence Berkeley National Lab. I have a student who's now there doing integrated mountain hydroclimate. And so I'm very proud of his success, and I think that many of these students have a very promising future in research.
So Ruby, how did you get started in research?
Yeah, how I got started. Yes, so by going to graduate school, so I decided to pick a topic. Well, my undergraduate degree was in physics, and so when I picked a topic for graduate school, I feel that I wanted to do something that I can use and connect better with the environment that I know of. So I started studying atmospheric science, and then later on when I joined Pacific Northwest National Lab. So that was the time when there was a lot of discussion about climate change. But at that time, that was many years ago. At that time, climate models were run at very coarse resolution. So we weren't able to resolve mountains and valleys and things like that. So then I started doing research to develop models that allow us to look at the impacts of climate change, how to translate climate information at the larger scale that we can then use to inform decision about how we manage water resources, how we look at the impacts of climate change on ecosystems, on agriculture, etc. So currently we have been, I've been working with a really big team of scientists developing an Earth system model for Department of Energy to support the energy mission. And so with that, we have been working across scientists with many different disciplines, because an Earth system model requires us to represent all the different processes in the Earth system. And that's not only processes in the atmosphere, but also processes in the terrestrial system, like the vegetation, the soil, but also the ocean, the sea ice, and the cryosphere processes. So working across a team like that really help us to better understand the Earth system. But then, as you said, there are lots of challenges, because even though I myself may be an atmospheric scientist and I know about the atmospheric processes, but an Earth system model is not just about the atmosphere. So we need to make everything work together. And these are some of the bigger challenges that we have been facing. Yeah.
Thanks. So I'm just going to kind of reiterate. I'm Charlene Weatherwax, the Department of Energy, and I'm here talking about climate science with Ruby Lung from PNNL, Rao Kotavarti from Argonne National Lab, and Paul Ulrich from UC Davis. And we're just having a little discussion, finding out, how they got to where they are now and what are the big challenges ahead. So Rao, how did you get started in what you do?
Yeah, I grew up in India, and I actually have a degree in chemical engineering. So the first job I had was actually producing aspirin in a chemical factory in India. And it was amazing to see how the aspirin was produced. Actually, aspirin is one of the most complicated things to produce chemically. And it had so much, it used phenol and sulfuric acid, 98%. And the phenol was basically dumped into the ground in groundwater. When somebody drilled a hole, its phenol was coming up. So that made me realize, man, there are other things into life than doing aspirin. So that's why that made me start looking at pollution and effects like that. And that's the start of my getting into this field.
That's great. That's great. Yeah, a lot of times things that you see when you're growing up really influence your decision on what you want to do with your life, right? So Paul, how about you?
So I actually have a bachelor's degree in computer science and applied math from up in Canada, actually. And I had an interest in kind of doing fluid mechanics, kind of astrophysics type work, and actually ended up doing a master's degree in theoretical cosmology. So I always joked with people that I'm kind of like a master of the universe type person, for those who get the 80s reference. Anyway, so after that, I realized that although it's scary to think in billions and billions and billions of years, trillions of years, that the universe may eventually sputter out, we got much more pressing problems kind of closer to home in the near term. And I really wanted to dedicate my knowledge and expertise to actually tackling some of these problems in kind of near-term risks in the climate system. And so I turned my attention to atmospheric science, because even though I had this broad interest in kind of planetary atmospheres, the Earth's atmosphere is probably one of the most interesting, just because of the complex processes involved and the different species, water that we need to track through the whole system. And so I got involved with that, applied my computer science knowledge, and started developing models kind of from the ground up, solving the very primitive equations that actually govern fluid motion in the atmosphere. And from there, started learning about all the different facets of the Earth's system and the different processes that are involved, eventually intertwining that and even branching out into this stakeholder outreach that I'm involved with now. So it's been a windy path, but I feel as though I'm learning more and more every day about the complexities of the Earth system.
That's great. So what do you think is the biggest challenge immediately facing you in what you do? And maybe I'll go back to Ruby.
Okay, I think one of the biggest challenges we are facing as a climate scientist, and also as someone who model the climate, is that there are lots of uncertainties, right? So just like everything in life, uncertainty is inevitable. So uncertainties are also there in the climate models that we are developing. So how do we communicate the uncertainty in projecting future changes in climate? And also, but understanding like, what are the different types of uncertainties? What can we do about those uncertainties, and how do we communicate them? I think that alone requires a lot of research effort, but also great communication skill when we talk to different audiences to explain where the uncertainties are coming from and what we can trust, and perhaps things that we may not be able to trust so well, because currently there are limitations in the approaches that we are using. So I think really understanding, characterizing uncertainty and communicating uncertainty is one of the biggest challenge that we have.
All right, I'll throw that question at you, Paul. What's your biggest challenge currently facing you?
I would say my challenge is probably pretty similar to the challenge that many climate scientists have. Not enough data, not enough computing power. Department of Energy has amazing supercomputing facilities, and being able to leverage those has really pushed the science forward. But for as much as they have, we can always look for more and use that additional computing power in order to answer deeper and deeper questions. And we need more data We need more. I mean, if anybody's familiar with kind of machine learning methods, they are data hungry methods. And we use those actually in our research as well in order to understand relationships that exist between things like precipitation amount and stream flow or snowpack accumulation. And so the more data that we have, the better understanding and the more constraints we can put on the relationships that exist within that system, and thus get a deeper understanding of the system overall.
Yeah.
All right. And how about you, Rao?
Yeah, it's slightly different viewpoint because I'm working with community stakeholders. So often my challenge is listening to the community of our stakeholders' point of view, and then we're able to translate that into a scientific question that we can address with the fantastic computational, scientific, and analytical talent we have at the DOE laboratory system. And I find that developing this two-way stream of communication is complex, because it interfaces with socioeconomic, cultural, and environmental justice issues. And of late, I think one of the biggest challenges we will be facing, or I'm facing right now, and more people will be facing, is maintaining this focus on our primary mission of science and science as a service to society, while managing the expectations of the communities as what they want from us. So I think this is going to be a fine line we will be walking for a while. And how we do successfully is very important.
Sure. So it really is a partnership between you trying to getting the science to answer the questions that your local constituents need, right? Yes. So, and so Ruby's talked about climate on a really large scale, global scale, and then you're talking about local stakeholders, and then I hear Paul talking about talking to water utility folks. So climate can be relevant on a number of different scales, and so I'm wondering, how do you think about scaling what you do at the local scale to a larger scale? So I'll throw that at Paul.
Oh, that's a good question. So we do operate across scales in the types of questions that we answer, going all the way down to, again, things like mountain snowpack, which of course exists pretty much constrained to an individual mountain range. And in that context, of course, we need really, really high resolution models in order to be able to actually properly capture those processes. But kind of larger than that as well, we have to be able to capture the general circulation of the planet. That is, we have to be able to capture the jet streams and the wave motion that gives rise to the weather that we experience. But on a day-to-day basis, I mean, inevitably people do experience weather in their local domain. And so they want to get answers about how their local area is going to be affected by something like climate change. And so it's a challenge, I would say, just bridging that gap, bridging that knowledge between different scales within the system. And basically it's an open problem that we're constantly trying to tackle.
Right. So how could somebody who's just not a climate scientist, how could they get involved and help you in what you do? So Rao, I'll put that, you work closely with stakeholders. So how do people know to come to you with a problem?
Yeah, I mean, so we've been fortunate that we started working with some utilities and big companies like that and communities. And so that kind of gave us an entree into started talking to them. And a lot of people have realized that we have this we produce this really high resolution data set that it could inform some of these communities. So that has given me a chance to talk to these people and actually produce the data products that are needed for them. Going back to the question you asked before, so talking to one of the utility companies, they said, I'm really interested in icing on wires. From a climate wire model to an icing on a wire is a long, long way off, right? But that is a process question, right? When does the rain become ice on a surface? When it hits the surface, what conditions produce that? That's actually a process question. So now we can take it back and say, how do I put the conditions in a climate model that can produce ice, and how do I develop this process into that, and what kind of resolution do I need? So we can ask those questions. So I think getting involved with the community so they understand that I have a stake in what they think about this, in the sense that helps me understand my science better, and that I have something to give to them actually gives it a two-way streets, and that has been very helpful. And I think that's probably is the value here.
So Ruby, you work at global models, but then you also talked about flying through clouds to collect data. So for you, you've really been working on all scales, I suppose. So what is that like?
Yes, because there are so many processes in the Earth system, and we do need to understand all the processes across different scales. Particularly interesting is that when people think about climate change, usually they don't really think about, oh, what's the change in the global mean temperature, right? What they want to know is really like, okay, what will be the change in my local area? And more particularly, they are interested in changes in extreme events. Most people are interested in how tropical cyclones may be changing in the future, how atmospheric rivers, the type of phenomena that produce a lot of precipitation, or heat waves, these type of phenomena, how they might change in the future. And in order to simulate these type of extreme events, we really need our model to have high enough resolution, because these events happen at smaller scale. And therefore, we try to model these processes using higher resolution model. But as many of my colleagues, Rao and Paul already said, we do need to use data to verify that our model, even though we can go to very high resolution, but that doesn't necessarily mean that it can now produce everything that is correct. We still need data to verify our model and constantly use the data to improve our model across a whole range of scales, so that we can answer questions such as how climate change may be affecting extreme events, making heat waves more unbearable, making thunderstorm more intense, etc.
So keeping on that theme of extreme events, Paul, you live in California, where there've been a number of extreme events. And so tell me a little bit about what that means in terms of the kind of modeling that you do.
Yeah, being in California is kind of a constant reminder of the different extremes that one can experience. Obviously, we don't really get tropical cyclones here very much, even though that's a big focus of my research. But we do get atmospheric rivers, of course, and we haven't had a big atmospheric river in a long time, like we had in the 1860s, actually, that ended up basically flooding the California Central Valley. But we have had like a really big atmospheric river storm that passed through not too long ago here and basically dumped a huge amount of snow up in the Sierra Nevadas. And we had a major heat wave event. We had wildfires that have been growing in size and intensity over the past several years as well. And so it's important to understand the questions relevant to where these events will occur and what impacts they will have on infrastructure and on communities. So when it comes to flooding, we need to be able to ask, are our levee systems prepared for the types of floods that we are going to expect here? When it comes to wildfires, we have to be able to say, are our communities prepared? Where will these wildfires start? Where is most vulnerable to the occurrence of these wildfires? And then what are the downstream impacts? Wildfires, of course, are known in order to trigger, for instance, mudslides. And so we need to be able to know if a particular wildfire event has the potential then to damage infrastructure or communities through kind of these secondary effects as well. And so people remember extremes most, I would say, from weather. If you ask anybody of a major weather event that sticks in memory, inevitably they're going to name some extreme. And so in that sense, focusing on the extremes and the impacts that they bring with it is very important in our service to the broader community.
So Rao, you live in Chicago, so I know you know about weather extremes, not just icing on wires, but maybe you can expand a little bit on, what's the interest in extreme weather, especially for your stakeholders.
So this is a pretty challenging question in the sense that extremes for Paul are very different from extremes for somebody in Chicago. So in Chicago, we are talking about if you get 95 degrees Fahrenheit here, that is an extreme temperature. Houston, that is everyday temperature. So that is the challenge in talking about extremes. So for us in the Midwest, most of the models are predicting that the intensity of precipitation is going to change quite a bit. And by quite a bit, we are not talking about a sigma change or a delta change. We are talking about 100% change in a lot of events. So that has huge stress on a lot of the stormwater systems, drinking water, all the hydrological systems in this Midwest will be deeply impacted. So when we say extreme intensity of precipitation increasing, now I'm trying to tell people, I don't mean a little bit higher, I mean double of what rain you are seeing in an hour compared to now. So that is a completely different system. So I think bringing awareness of this and to people that we're not just talking about small changes here, but there could be very drastic changes. And even heat events, mostly we talk about heat events, they think there will be more heat events. People think there will be 3-day heat. Right now, heat event is defined as a 3-day event. You will think, okay, now we have 2, there will be 4. That's not it. It's going to be, duration is going to change. Instead of 3 days, you'll have a 6-day heat event. So the whole infrastructure that supports a community for a 3-day heat event will not work for a 6-day event. So you're thinking about extending the resources over 6 days. That is double the capacity you have right now. So these are very, very challenging questions, and these are the kinds of things when I talk to people and I explain, there is some realization. So my thing is trying to get to the point that, okay, these are important effects that you need to think about right now, not 30 years from now. These changes are happening as we speak.
Okay, so now I want to shift a little bit and think of it a little broader in time frame. So Ruby, when you think about your climate models, at the resolution that you're running them, how far out can you run them? How many years in advance do you think that we have a lot of confidence so that we can plan for infrastructure, as Paul mentioned? And how, what's the next step in terms of getting to a longer time frame that we can feel more secure about what we're projecting?
Okay, yeah, that's a really good question. So our climate models can be run for a very, very long time period. A lot of time, people might ask questions like, okay, what about the end of the century? How would our climate look like? But more often, people might ask like, okay, what about the next decade? How would the climate look like? And the climate models can be run to answer these type of questions, whether you're talking about like a century from now, or whether you're talking about just the next decade, or even just the next month, etc. It depends on what information we feed into our model, right? So when we are projecting far out into the future, the most important information we need is like how much greenhouse gases will be emitted in the future, whether we would be making a lot of changes to the land surface and the land cover, will we be growing this type of crop versus that type of crop, or converting the land to be urban areas, etc. So those are all important information in order to project far out into the future. But if we are interested in asking the question like what might happen in the next decade or in the coming season, we feed a lot of information about what is happening now, because what is happening now fit into what is happening in just the next month or the next decade. And so having this information, the data coming from the ocean, is our ocean already warming up? Is the land surface or the soil moisture particularly wet now? And these are really providing some memory, because these processes are pretty slow, happening rather slowly. And if we know what is happening now, they provide us with information about what might happen next month or in the next decade. So it all depends on the information we feed into our models. But of course, further out into the future, we are not exactly predicting what might happen, but rather we are providing scenarios of what would happen, because a lot of the outcomes far away in the future depends on what we do now. So it's not like set as in stone, right? Because if we continue to emit greenhouse gases the way we do, or we determine to intervene and do something else, that would have a big consequence to what might happen far out in the future.
Right. And so of course, we're really putting a big push in to reduce emissions now, reduce carbon emissions, right now. And I'm wondering if you can say, Paul, what impact do you think that would have on the kind of modeling that you do? If we were to really, go in, go for clean energy, really, cut, find alternatives for our big carbon emissions now, what could that do for us? And would you be able to see that in your model?
Oh, I'd be very excited if we were able to reduce our carbon emissions. If climate science has taught me anything about the way that the system operates, is that simply these carbon emissions and our pollution into the atmosphere is having an immense effect on the overall climate system. And we're going to be feeling it for years to come. The modeling that we do looks at everything from kind of best case scenarios to worst case scenarios when it comes to overall carbon emissions. And so we have kind of our business as usual type scenarios where we project if there are no constraints put on overall carbon emissions, what is the climate impact going to be associated with that? And we can see some pretty extreme impacts by the end of the century on everything from extreme heat to precipitation change, loss of snowpack, loss of sea ice, basically implications globally in that scenario. But we also do model kind of the more optimistic scenarios, of course, so that we can understand how much better the system would be or how much we can recover from kind of this pre-industrial if we actually did more aggressive action in order to cut down on carbon emissions. And in that case, we can then recover and say, well, this is what we think that the climate system will be like 100 years from now under that particular scenario. With that said, inevitably, this modeling doesn't only answer questions related to global temperature change or extremes under carbon emissions, but inevitably we'll also be having questions like if we have widespread deployment of renewable energy systems, whether those be wind turbines or solar plants, how are those going to be affected by future weather as well? So wind turbines plus icing, for instance, as Rao mentioned, what are the consequences associated with that? And those are all questions that we can answer with our climate modeling systems too. And so this deeper understanding of the processes that exist within the Earth system really opens the door to many, many interesting explorations on how the Earth system operates and how we interact with the Earth system in kind of like a human Earth system context.
All right, Rao, do you have anything else to add?
Yeah, just one point. I'll just try to pull the thread that Paul mentioned a little bit on effects. We can probably forecast on what happens to renewable industry, right? So if you're changing the thermal energy, thermodynamics of the Earth, so it will obviously affect your wind fields because you're changing the gradients. It can go either way. It can go higher or lower. But small changes, like systemic changes in 3% wind speeds by mid-century, either up or down, have huge impact on how we plan the wind energy future that we are thinking about. So it's a cube of the wind change is what the power is. So a 3% change in wind is a big deal. So we cannot predict everyday thing, but we can predict systematically whether there will be a decrease as we go in the future in a place that is wind rich right now. And if a 3% decrease in wind happens there, what will happen? So these kind of questions we are actually prepared to do right now, and we are trying to do, and I think that's where we are right.
Well, I think this is really exciting. I mean, we've heard a lot about a lot of different types of energy sources, the impacts of climate change on energy infrastructure. And I think some of the work that you're doing, really indicates that everybody's got some kind of role to play, and that even if, that all of these will have some kind of impact. And then we'll be able to see that run out in these scenarios that you do over maybe a decade or 100 years from now. So I think that gives me a lot of hope that we're on the right track to at least be able to see that the small changes can have big impacts later if we all do our piece. So maybe I want to just ask something kind of fun for a change. So what's the most fun thing that you've done in your job that maybe you wouldn't have expected? I mean, so maybe it's fun for you to sit at a computer and code, but maybe there's something like really fun and unexpected that you've had to do in your job. So I'll put that at Paul, since he's the computer guy.
Yeah, I mean, again, I had a background in computer science and applied math. If you were to stereotype me, you would say you're probably the one who should be kept as far away as possible from stakeholders as possible. But instead, I find myself here basically interacting almost daily with practitioners and stakeholders, understanding their needs and being able to talk to them. And I find that I just enjoy it immensely. Being able to answer their questions, being able to use their questions as fodder for deeper research explorations, looking at the data that we have and being able to kind of turn that knowledge into real answers that they can actually act on. So just having the opportunity to talk with practitioners application scientists and understand their needs has been really a big change in my career trajectory overall. And I find that it's just been very fun in the whole time.
How about you, Ruby? What's the most fun and unexpected thing you've had to do in your job? Maybe I'll put that question to Rao, and then we'll come back to Ruby.
Yeah,
so Rao, what about you?
Early in my career, when I started working on atmospheric, I started as an atmospheric chemist. I had an opportunity to fly on a DC-8 that was operated by NASA for something called Pacific Chemtropics. So the plane was, our base was in Australia, near Australia, and we were flying maybe 1,000 feet above water for several hours. Oh, wow. It was crazy. This is a huge plane flying, and you see these little islands. Nobody can live there, but there are these little islands in the Pacific that looks like brilliant diamonds, and then you see this green. Oh. It was the most amazing thing I've ever done in my life, and completely because I came into this field. Otherwise, I would have never had the opportunity. Yeah.
All right, Ruby. So how about you? What's the most fun and unexpected thing? And you can tell another plane story if you want, but maybe it's something else.
Plane stories are the best.
I will use the plane story, but then another one. So yeah, several years ago, I was able to lead a field campaign where we were studying atmospheric rivers. As many of you know, atmospheric rivers, they dump lots and lots of precipitation, and we try to understand like what are the cloud processes that produce these heavy precipitation. So it was really fun for me because I am mainly a computer modeler. I develop models and I run model. So when in our model, we represent the clouds and we represent the cloud droplets in certain probability distribution. But I don't actually know how they look like, right? But flying through the clouds in the aircraft, you know, whoa, so this is what it looks like. And that produced this distribution of particle sizes and things like that. So that was really a lot of fun. But secondly, I enjoy a lot in a lab environment where we work a lot in a team setting. I think this really makes my research a lot of fun because I can see scientists with different expertise, different experience, working together, and that really allow us to address big problems, right? Because we have all these challenges that we are facing. We mentioned about uncertainties in the model. We need to run model at high resolution. We need to represent many different processes in our model. Now, together with a big team, we are to really put people to work who have expertise in the atmosphere, who have expertise in the ocean, and together seeing how all of these come together in our model and making that work, I think to me is a lot of fun.
That's great. So you know, I think we're probably getting toward not quite, but what would be something that you could tell somebody who is thinking of going into climate science, you know, to encourage them or tell them the kind of background they need or something like that? And so maybe I'll start with Paul.
I guess my first response would just be do it. We need climate scientists. We need people who are passionate about not only understanding the climate system, but passionate about the potential impact you can have on how people operate and how you can inform them about the knowledge that we have about the climate system. I would say that we have opportunities regardless of background, everything from communications through kind of the hard math or computer science involved in actually modeling the climate system. Even understanding the system requires different expertise ranging from like plant sciences. I've not mentioned this before, but I mean, one of the major outstanding questions that we have is like plant response to carbon dioxide emissions. It's not simply through heat that we are going to experience change because of carbon dioxide concentrations. And so if you're interested even in horticulture, then there's an opportunity for you to make an impact on the field. And so just any diversity of input, any diversity of discipline will benefit our understanding of the global Earth system.
That's great. Rao, do you have anything to add? What do you think?
Yeah, a few years ago, I was at a University of Chicago meeting where they asked me this question, what should I do? So the meeting was organized by public health students. So I told them, learn physics, chemistry, and biology. They were not too happy. Uh, but, but I think it's kind of changed a little bit now. People who don't know these things also can understand, should participate in this. This is a wide open thing right now because we are looking from everything from economics all the way to how it impacts the communities and science. So I think it's a very wide field. And I don't think if you anybody should be able to enter this field and contribute to it. And this is going to be the grand challenge for the next 50 years at least. So you will be secure if you get into this field and make a name for yourself. Then nobody. So that's my feeling. Yeah.
What do you think, Ruby?
Yeah, I think this is really a golden time to get into our field because the society now more and more we recognize the importance of understanding climate change and predicting what might happen in the future. So there are lots and lots of resources now from the government agency, from the private sector, all devoting resources to address this grand challenge problem. And besides resources, we are also at the verge of really making a lot of, potentially making a lot of breakthrough. We have big computers. Computers are really getting bigger and bigger. And Department of Energy, we are thinking about like next year, we might have the first exascale computer coming online. So these big computers allow us to run our model much faster and go into much higher resolution. But at the same time, there are many techniques, many tools that we are able to use now, such as like machine learning, artificial intelligence. I think it's really all of these coming together with the resources and the tools. So we just need the people. We need the next generation to help carry the torch. I think this is really an exciting time to get into this field.
That's great. So I know that the department is really committed to increasing the opportunities for everyone. You know, certainly they're very committed to diversity, equity, and inclusion. And so, you know, I know that each of you works in teams of different people. And so maybe you can speak a little bit about that. You've talked a little bit about different disciplines, but I know that each of your institutions certainly has something that's addressing DEI and how you think that that would benefit climate science. So I'll go with Paul.
Yeah, even in my lab, I would say I've got a pretty diverse group of students that I work with, and I'm very glad for it. The diversity of opinions and viewpoints that comes associated with that diversity is just fantastic, even if it just allows you to look at a problem in a slightly different way. But across all of Department of Energy, I mean, I interact with people with all sorts of backgrounds, whether that be academic backgrounds or ethnic backgrounds, and just having the opportunity in order to hear their perspective on the issue allows us to get kind of a deeper understanding or come up with new ideas or be able to brainstorm solutions to some of these problems that may be more suitable for particular communities or groups in a more targeted and more effective way. And so the efforts that we've made so far, I think pushing for DEI have been very beneficial, I think, in terms of increasing the quality of our output as well.
What do you think, Ruby?
Yeah.
Anything to add to that?
Yeah, increasing the diversity is definitely very important. And I know most universities and national labs, we have many different programs. Just want to mention, for example, at PNNL, we have a program called Young Women in Science, where we promote high school students, female high school students, to gain the experience of working in a national lab. I've also supporting the GEM Fellowship to work with underrepresented graduate students. So there are lots and lots of opportunities for really increasing diversity.
So we've heard a lot about some of the I think the standard disciplines, right? And some of the so what about folks who are not straight in science? So what about people who have backgrounds in, I mean, so Rao, you mentioned public health, you know, but what about somebody who's in like who has an environmental policy background? Like, you know, could they get involved with climate modeling and climate science also?
Yes, we desperately need them to get involved, actually. So, so one of the things I said before, talking about communities and climate impacts, it's highly likely that the communities that get impacted may be minority communities around the country and around the world, different communities. Even in a country like India, the people that get affected will be the poorer people who are in not well situated, right? So I think more people, more of those community getting involved in science is the one way to make sure that there is equity in how the science is done. So it is one way for me to talk about how this should be. There should be equity in the science we are doing. It's another thing somebody from that community joins and make sure that it is done. I think that is a great opportunity in the labs. There are so many programs for students. Right now is the season for applications for graduate students, undergraduate students. There are so many of things going on. Look at any of the DOE lab site and see opportunities for students. You will find tons of them. And there are some specifically designed for minority students, some specifically designed for community colleges. So there's a wide land of opportunity within the DOE system is very, very significant. And we are more interested in getting actually this going even bigger. So I think anybody interested should contact any of the labs and they would be quite happy to help you out.
Okay, do you have anything to add to that, Ruby?
Yeah, I want to particularly mention that in our field, very early on, we focus on climate change, right? But in fact, it's not just climate change, it's global change, because climate change is only one aspect. A lot of the changes that we are seeing is a combination of changes that are induced by human activities, and then we, as a society, we can cope with climate change, and we also need to intervene with climate change. So our field is not just about the physical system. We're gaining the knowledge about the social system, how people respond, and what we do, and how we better manage the resources. All of these are part of global change and how we might make our future better. So we really need a lot of expertise, not only in the physical science area, but in many different areas, in social science, in biology, in many other fields. So we look forward to working across a much broader disciplinary areas.
Okay, well, so I think we are up in time. So I just want to thank my guests today, Ruby Lung from PNNL, Paul Ulrich from UC Davis, and Rao Kodamati from Argonne National Lab. And you heard it. You heard that climate change is happening. We're modeling it. We've got bigger computers. We need more data. We need more people. We need lots of different kinds of people. We need people from horticultural scientists to, public health scientists to sociologists. We need them all. And so, I think that certainly I would encourage you to look at internship opportunities through the Department of Energy. And there's lots of opportunities to get involved. You're never too young to get involved. You're probably never too old to get involved. So I want to thank my guests and thank you all for listening. And I think I will sign off now.
Thank you.
Thank you.
Thank you.